Hello, welcome to Electronics Education. This is Vincent Chang. In this lecture, we are going to continue our study on the subject of feedback stability. The stability of feedback. Stability of feedback, part 2. Bode plot, gain margin, and the phase margin explained. Bode plot, gain margin, and the phase margin explained. So, why there's a stability issue here? So, two issues. Number one, feedback. In other words, you might be wondering when I should consider if there's an issue with the circuit. Two conditions. Number one, if there's a feedback. Number two, if there's a frequency-dependent situation. The frequency-dependent situation, okay? So feedback and frequency-dependent situation makes this an issue. To tackle this issue, you just focus on one quantity, complex loop gain. The complex loop gain, magnitude of the loop gain, and the phase of the loop gain. Magnitude of the loop gain and the phase of the loop gain. And also you focus on one frequency, omega pi. At this frequency, the theta of the loop, the phase angle of the loop gain turns into 180 degree or negative 180 degree. So which means at this frequency, the loop gain becomes the negative. So negative loop gain turns this circuit into a positive feedback. So at this frequency, the circuit becomes a positive feedback. Three scenarios, three possibilities. To ensure the circuit remains stable, then at this frequency, its magnitude, the magnitude of the loop gain has to be less than 1. Has to be less than 1. And then, if at this frequency, the magnitude of the loop gain equals 1, which means the circuit will have the sustained oscillation. Will have a sustained oscillation. And last case, last scenario, if at this frequency, the magnitude of the loop gain is greater than 1, then the circuit will oscillate with a growing amplitude. So growing oscillation, the circuit becomes an unstable. So three scenarios, stable, unstable, and oscillation. Stable, unstable, and oscillation. So now let's apply. Let's just get what we learned before and try to just look at two cases of practice. The first case on the left, the L represents the loop gain, the complex loop gain. So the diagram, the response on the top is the magnitude frequency response of the loop gain. The diagram on the bottom, theta, represents the phase angle of loop gain. So in terms of frequency, the frequency-dependent behavior is described here. So it's the phase response of the loop gain. So when frequency changes, and then magnitude gradually decreases, and also the theta also changes. So this is case number one. So what about the case number two on the right? The case number two on the right, a little bit different. On the frequency scale, you see the magnitude, the relationship between the magnitude and the phase also changes. All right, it's changed. So now I want you to make a judgment. Which one is stable and which one is unstable? Or both are stable or both are unstable. Is there any cases where the oscillation happens? The boundary between the stable and the unstable happens, which means that at this frequency, the omega pi, or at f pi, the loop gain is exactly equals to 1. All right? So I want to pause, maybe just quickly draw these two diagrams or take a screenshot and think about this for maybe just 1 minute. So let's pause for 1 minute. The question is quite easy, right? It's quite easy. So let's look at the first case on the left. The first case on the left. So you just focus on the frequency. So at this frequency, what frequency? F pi. At this frequency, the theta turns into 180 degrees. And at this frequency, the corresponding magnitude on the top falls below 0 decibel. The 0 decibel at log scale is equivalent to the 1 in linear scale. So at this frequency, the lobe gain falls below 0 decibel in the log scale, which means at this frequency, the magnitude of the lobe gain is less than 1. Is less than 1. At this frequency, the magnitude of the lobe gain is less than 1. Stable. So it's stable. But on the other side, on the right-hand side, it still also focuses on the frequency f pi. And this frequency, the corresponding, the f pi, on the right-hand side, all right? On the right-hand side, this frequency, the corresponding magnitude of the lobe gain is greater than 1. It's above 0 decibel. It's greater than 1. It's greater than 1. Unstable. So the stable for the left-hand side and the unstable for the right-hand side. Now, I'm going to teach you another viewpoint. The one I just mentioned, the one I just illustrate in the previous slide is the first viewpoint, all right? Focus on the f pi. Now, I want you to maybe change a little bit, change focus a little bit, focus on another frequency called FTL. Let me explain this notation for a little bit. Usually, the FT describe the unit gain frequency. And L, the second subscript, represent the lobe gain. So FTL represent the unit gain frequency of the lobe gain. In other words, at this frequency, the lobe gain drops to unity, 1. Drops to 1, equals to 1. At this frequency, the magnitude of the lobe gain equals 1. So at this frequency, FTL, the corresponding phase is within 180 degrees. Or the magnitude of the absolute value of the phase angle is less than 180. So pay attention to the absolute sign of the phase angle at this frequency. What frequency? Another frequency, all right? FTL. At the unit gain frequency, the phase angle, the magnitude of the phase angle at unit gain frequency is less than 180 degrees. Then it's stable. But if at this frequency, FTL, the unit gain frequency of the lobe gain, the corresponding phase angle surpass over 180 degrees. Over 180 degrees. So it's unstable. So this is the second viewpoint. All right? So I want you to get familiar with these two kinds of viewpoint. You can use either one. But sometimes the second one, in some cases, is more convenient. All right? This is why I teach you the second viewpoint. Of course, you can, if you have get used to the first one, there's no problem. There's no wrong with that. But sometimes for the sake of convenience, so we prefer, in some cases, we prefer the second viewpoint. So now, let's go back to another, it's called PM. Well, what is the PM? So let's say if this is your circuit, and I said, I kind of challenge you, have you considered the stability of the circuit? You say yes. So I said, at the unit gain frequency, what's the phase? And your answer is, Vincent, 178. 178. What does that mean? Yes, it doesn't surpass. It's within the 180 degree, right? But only 2 degree margin. Only 2 degree margin. You get it? Only 2 degree margin. You get it? Because for the circuit design, we have to consider the variety, the environment, the temperature. So when the temperature changes, the environment changes, or noise get involved, the curve will fluctuate it, right? The curve will fluctuate it. So at this scenario, at this situation, in this temperature, at this temperature, maybe it's stable. But when temperature change to another, you change the environment, you change temperature. Maybe now, before it's the 178, and then it turns to 190. So that means the margin is not sufficient enough. The phase margin is not sufficient enough to guarantee the reliability of the design, of your stability design. We have to guarantee the sufficient enough the phase margin to against the temperature or environment changes. All right? So this is why we need to quantize, need to specify the phase margin. So sometimes within 180 is not enough. So usually for the industry standard, usually we take 45 degree of phase margin, 45 degree of phase margin. For the gain margin, another one still. So on the phase diagram is the phase margin, the definition of phase margin. Also, the green part is the definition of gain margin. At omega pi, f pi, at the f 180 degree, the magnitude of the loop gain, the difference between the magnitude of the loop gain and the 0 decibel is how close you are approaching to the boundary, the critical condition. So it's the gain margin, all right? So make sure you grab this too. So we will talk about this, or you will be asked to analyze this in the future. So what is the phase margin? What is the gain margin? As an IC designer, and sometimes in the spec, the specification, the phase margin or gain margin will be given. Then you have to come up with the design to meet the requirement, the specification of the phase margin and the gain margin, which describe the stability. Now, how stable your circuit is. How stable your circuit is. Phase margin and gain margin. Takeaway. First takeaway. The first viewpoint focus on the F pi and compare the magnitude of the loop gain with 1. With 1. If less than 1, stable. And greater than 1, above 0 decibel, as the unstable. Takeaway number 2. The second viewpoint focus on the unit gain frequency. At this frequency FTL, the magnitude of the loop gain drops to 1. Drop to 0 decibel. The corresponding frequency is called FTL. And at this frequency, at the unit gain frequency, if the theta, the angle of the loop gain, is within 180 degree, then it's stable. But if it's over 180 degree, then it's unstable. So we have to come to the end of the lecture. Thanks for watching.